Excuse me, sir. Just 2 minutes. You can stop your presentation, sir, so that our admin team will show the slides, sir. Just 2 minutes. Yes, sir.
Yeah.
Good morning to one and all present here. I welcome all the participants to this Phase 3 6 days short-term training program on nanotechnology and functional materials. Now we are going to start 4th day and the first session. Once again, thank you for joining with us. Now let me introduce our resource person, Professor Dr. Sudarshan Ghosh, Professor from Department of Mechanical Engineering, IIT Delhi. He has published more than 400 research articles in reputed journals and conferences. He has a citation having 1588, H index 21, I index 40. He has completed many research and consultation projects. These are the few glimpses. He has delivered 12 master level courses in manufacturing engineering using two-way video conference mode. He has developed a cryogenically coupled vibratory EDMP process to machine hard materials and conducting ceramics. He worked on improving grinding characteristics of titanium alloy using nanofluids under minimum quantity lubrication technique and liquid nitrogen jet. He worked on prediction of cutting forces, surface quality, and tool wear in end milling. We are honored with your presence, sir. Now I request our resource person to continue with the session, sir. Requesting, sir.
Thank you for giving me this opportunity to show you some glimpses of the research work which we have been doing at IIT Delhi. So it will be my pleasure to share with all of you the work which we have been doing, and we are continuing with that same work. And I hope that the talk which I will give today will actually make you more interested in this type of work, and at least some of you should try to work in the particular domain, which is basically the usage of the nanofluids in machining and grinding. So let me share my presentation. So hope you are all able to see my presentation.
Yes, sir. Yes, sir.
Yeah. So good morning to all the participants and the organizers of this workshop. So today I will be presenting a talk which is on the application of nanofluids in machining and grinding. So we have been doing this particular research on the nanofluids for the last 6-7 years, and almost like 3 of my research students, they have also graduated. Also, they have submitted their thesis and they have graduated. So they have worked in this particular area. And in fact, I will be showing you glimpses of the work which we have done at IIT Delhi during this entire course. So now, before we start on this application of nanofluids, let us try to understand what is the motivation. Why there was a need for these nanofluids, and what are these nanofluids, and why at all we should use these nanofluids in machining and grinding. So to understand that, let us go through quickly through the machining process. So here, as you can see, this is an image which I have taken from some source. So from internet source. So you see, this is typically a internal turning operation with a cutting tool, which is basically a coated cutting tool. And as you can see, it forms chips. So the mechanism of formation of chip is also shown in this particular schematic diagram. So we have a cutting tool which is normally harder than your work material, and the cutting tool has some specific geometry, because of which once you have the relative motion between your workpiece and the tool, material from the workpiece, it gets removed, and the removed material is called as chip. So in picture, everything appears to be very good. And then obviously the question arises, then what is the issue? If we give the right geometry to the cutting tool, we can definitely machine materials. What is the problem? Now we have to understand what are the issues in such metal machining processes. Now for the common materials like mild steel, the machining is not difficult at all, right? So there is no issue. So everything will go very smoothly. The material will get removed from the workpiece, and we will get the desired shape and form of the product. But then these days we do not use the mild steels in many applications. In most of the engineering applications, we are going with using of some alloy materials. So they may be alloy steels, they may be alloys of other materials also. Not iron-based alloys, there may be also some other based alloys like aluminum-based alloys or magnesium-based alloys or the titanium-based alloys, right? And such alloys, they have these properties which you see, which is high hot hardness and high strength. That means these new types of alloys, they possess this property of hot hardness and high strength. What is this hot hardness? Hardness, we understand the resistance of a material to penetration. So if we try to penetrate into the material, so the material will give some resistive force. So that can be computed, and that is termed as hardness of the material. Now, what is hot hardness? Normally, for most of the materials like steels, the mild steels which we were discussing, so for these materials, once you increase the temperature of the material, the hardness of the material increases. But these new types of alloy materials which have come out and which are getting popularly used in engineering application, for them the situation is a little bit different. So for them, even if you increase the temperature, the hardness does not fall. So that is what is meant by high hot hardness. So this hot refers to at higher temperature when we are measuring hardness. So that is what is referred by hot hardness. And high strength, you can very well understand that this is basically the ultimate tensile strength of the materials, which is normally referred to. So normally these new engineering alloys, they have high strength. Sometimes, these super alloys also possess some hard carbide particles in their microstructure. So these hard carbide particles, when we are trying to machine the material or the alloy, so what happens? These hard carbide particles now hits your cutting tool. So though the cutting tool material is hard, but even then these carbide particles are also almost equally hard. So what happens? When these hard carbide particles impacts on the cutting tool, then there is wear on the cutting tool, which is mostly, there are various categories of wear, but this wear which normally happens when the hard carbide particles impacts the cutting tool is basically the abrasive wear. So what happens during the machining process of these alloys, which we can also call as super alloys. So for machining of these super alloys by the standard cutting tools, there is a good amount of wear on your cutting tool surface. So now once you have high wear of your on your cutting tool, what happens that after sometimes you need to stop the machining process and change the cutting tool. So you see there is a lot of wastage in terms of the productivity of the process. So once you stop the machining process, obviously the productivity gets hampered. So this is one major drawback. And also, of course, once you are using a new cutting tool, obviously the cutting tool, you have to pay for the cutting tool. The cutting tool does not come free of cost. So that is of course also there. But more than that, it is the loss in the productive time, which is very detrimental for the industries. Now, there are other issues other than this abrasive wear of the cutting tool. There are also other issues like these super alloys, which may be of nickel based or titanium based, or sometimes also iron based super alloys. So they also form what we call as built-up edge on the cutting inserts. Now, once this built-up edge forms on the cutting inserts, what happens? The geometry which we have given to the cutting tool, right? So that geometry gets lost. So now once the geometry of the cutting tool is lost, then the efficacy of the tool or the efficiency of the cutting tool in removing material also degrades. So this again is an issue in the metal machining processes. So as you can see, the built-up edge not only deteriorates the tool, but it also sometimes impairs the quality of the machine products. So the surface finish of the machine products that get also hampered. And then other than these effects on the cutting tool, on the work material itself, you have some effects which are very detrimental. So like work hardening and shear stress localization of the super alloys takes place. And because of the work hardening phenomena, so work hardening is something like, if you can recall, work hardening is sometimes one of the reasons for work hardening is basically dislocation jamming. So what happens, as initially the machining will be very smooth, but as time progresses, as the material gets work hardened, so what happens? The machining becomes more and more difficult. So the cutting forces during the machining process will tend to rise when you have materials which are work hardenable. Of course, all materials are not work hardened, but as I am telling you that mostly the super alloys have this issue that it can become work hardened easily during the machining process. So now these are all the difficulties during the machining process. But then these super alloys needs to be machined because products have to be formed out of these super alloys, and we really do know that a lot of products are getting formed from the super alloys, and they are finding applications in various industries, including the aerospace industries, the biomedical industries. So obviously products are getting manufactured out of these super alloys, and many of these products for the manufacturing process, the only method is basically your machining operation. So then the question arises that how is it possible? So you can see over here that for the last several decades, it is some cutting fluids, or what we call as metalworking fluids, which are being used very rampantly and widely, and it has been proved also the use of these types of mineral-based metalworking fluids can enhance machinability. So this is mineral-based super alloys and the mineral-based metalworking fluids to enhance the machinability of the super alloys. Now, the super alloys, it's not always that the super alloys are always after the machining operation, some grinding operation also needs to be done.
Sir,
So here is a
excuse me, sir.
image of a, yeah.
Excuse me, sir. Sorry to disturb you, sir.
Yeah.
Due to
Please.
some unstable network, it seems that we are not getting your voice clearly, sir. You can switch off your video, sir. We can able to continue, sir. Just,
okay,
so that the network utilization will be less. Yes, sir. Yes, sir.
Right. Just a minute. I'm switching off my video and then
Yes,
I will be sharing my screen. Okay.
Yes, 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 sir. Yes, sir. Yes, sir. Thank you, sir.
Are you able to see my screen?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Perfect, sir. Perfect.
Thank
Presentation
you.
mode,
Thank you. Yeah. Thank you. So this is what I wanted also, because sometimes when I am speaking, I do not know what is the problem from your end. So,
yes,
so that is the thing. Please.
Thank you, sir. Thank you, sir.
So as we were discussing that sometimes these super alloys not only require machining. After the machining, in order to give them, say, better surface finish, sometimes we have to do grinding operation. So grinding operation normally provides better surface finish and also it provides a better dimensional accuracy. So for some precision components, it is very, very important that we have to do a grinding operation after the machining process. So grinding also needs to be performed on these super alloys, and this is an example of a grinding which we were doing in our lab. So you can see these sparks which are coming out. So these sparks are nothing but the chips. So in machining also we have observed the chips now which comes out, but in machining the chips are they do not form such coloration or sparks. But in case of your grinding process, such colorations happen mainly because the chips are tiny in shape and the temperature during the grinding process is so high that these chips reach the melting point. So these sparks are nothing but the melted chips which are coming out. And why such melting or such high temperature happens in the grinding process? A quick recollection of that. If you see this particular schematic diagram on the right hand side, you can understand that here, instead of cutting tools, you have the grits. So these grits are actually, they do not have the shape. They do not have the requisite shape. So that is the reason why you have there is a high heat generation, because the shape is not there. So that is the reason. Just a minute, am I online?
Yes, sir. Yes, sir. Yes.
Hello.
Yes, sir. Please, sir. Please.
Yeah. Okay. So that is the reason why the high heat generates. It is mainly because of the shape of the abrasive grains which acts as the cutting tool. So these abrasive grains do not have the requisite geometry and shape, and it is primarily because of that you have very high heat generation during the grinding process, and that is the reason why you have this type of sparks coming out. So here also there is a heat issue. So whatever issues we have discussed for the machining, the problems associated with the machining process, for the grinding process, the same problems exist, or on the other hand, actually some of these problems becomes multiplied. So in the grinding process also, the only alternative is to basically use the metalworking fluids during the grinding process. So if we take a quick look at what happens during the machining or the grinding process, you see a lot of heat generation happens during the machining or the grinding process. And there are two sources of this heat generation. One is because of the deformation, because as you know, in the metal machining or even in the grinding process, there is, especially when you are machining the superalloys, which are ductile materials, for them there is a good amount of plastic deformation happening, which is mostly the shear deformation which happens. And during this shear deformation, what happens? So shearing and cutting. So because of this shearing and cutting phenomena, a lot of heat is generated. Not only that, you see when the chip is flowing over the tool surface, so the tool's top surface is called as rake surface. So when the chip is flowing over the rake surface of the tool, there is a friction work taking place. So friction happens at the rake surface. Now, when it is flowing over the rake surface, a part of this chip also comes on the flank surface. So the flank surface is here. So a part of this chip will also be touching the flank surface. And this will also result in a friction at the flank surface. And this also leads to heat formation. But in this case, as you can see, in the metal machining case, the situation is a little bit better in the sense that your chip, which is basically the waste material, no? Because chip, we don't want chip. So once that material is removed, it goes out. So this chip actually carries away almost around 80% of the heat which is produced. Only say around 10% of the heat goes into the workpiece and the remaining 10% goes to the tool. So basically in the machining process, the chip is carrying away maximum amount of heat. So that in one way is better. But when we come to the grinding process, the situation is totally unfavorable. Also here the heat, the total amount of heat generated is also high, and as you can see, the only a small portion of the heat is taken by the abrasive wheel, that is the grinding wheel, and the majority of the heat is taken by the work material. So this is very, very detrimental. Why it is detrimental? It is detrimental because you see, once the work material gets heated, so the work material, the top layer of the work material, which is touching the grinding wheel surface, that will become heated first, and consequently, as we know, that when material gets heated, the material tends to expand. So when the material is expanding, what happens? As you go below the material, there is a temperature gradient. So the top surface temperature is high, but as we go inside, the temperature reduces. So the top surface tries to stretch out, the bottom surface is not stretching that much. And this phenomena of tensile residual stress within your work material. So this tensile residual stress remains. So this is a type of hidden stress also. So it remains within the work material even after the grinding process. So you understand the whole issue, that if such hidden stresses remains, then what will happen? Then the entire life duration of the component, of the ground component, will get altered. And normally these tensile residual stresses, they will lower the life, right? So they actually influence the fatigue life of the component. So if the designer has designed the fatigue life to be say 10,000 cycles, now because of these hidden stresses which get generated during the grinding process, if they at all get generated and they remain within the work material, then the life of the component may get reduced from 10,000 cycles to say 5,000 cycles. So that means almost by half the life will get reduced. So that is highly detrimental. And for some very critical components, it cannot be also you cannot afford those critical components that their lifespan can be reduced so drastically. So it is the best way out is basically to minimize or remove this heat generated during your grinding process. The same also holds true for the machining operation. So if we are in a position to basically lower down the heat generated during the machining or the grinding process, it is always beneficial. Now, some of the issues which are encountered due to such heating during the machining or grinding process have been schematically shown over here. So, of course, the one thing which I was telling you is the generation of the residual stresses. And the other thing is, as you can see here, the hardness of the material. The hardness of the material because of the high heat. What happens? The hardness of the material also, there is a gradient or change in the hardness of the material from the top layer towards the bottom layer. So the top layer being highly heated, they will lose their hardness. So in the top layer, the hardness will be less, whereas as you go inside the work material, the hardness will be more. Not only that, the microstructure, if you see, the microstructure can also get altered because of the high heat. So once the temperature becomes more than almost the half the melting point of the work material, what happens? There is a tendency of the grains losing their shapes. So there is a grain regrowth which happens. So because of that grain regrowth, what happens? The texturing or the grain structuring of the work material on the surface and inside, there will be changes. So normally on the surface, the grains will be of larger size, whereas on the inside, the grains will be comparatively smaller in size. So here is an example. If you see on the right hand side where I am pointing with my laser pointer, you see this is an example of titanium alloy Ti6Al4V. This is a very popular titanium alloy which is being widely used in various industries. And this material has been ground by a grinding wheel of composition aluminum oxide. And after the grinding process, the surface was basically scanned in a scanning electron microscope. And you can see that on the surface, you have a lot of crack generation. So these cracks which are formed, as you can see in the schematic also, these cracks are again due to the thermal expansion and contraction created by the high heat generated during the grinding process. So the essence of all this discussion is that in the machining or in the grinding process, we somehow have to lower the heat generation. So now how it is possible? So heat generation, one is this shear deformation process or the cutting process. So that will obviously that will happen. So we do not have much control on this. So we do not have much control on this. Whatever heat will be generated. So the only thing which we can do is this heat which is generated because of this shearing process or the deformation process. If we can have some external means like the metalworking fluids to take away that heat, then it will be beneficial. Now coming to the friction part, so in the friction part we can play with the friction part in the sense that the rake surface and the flank surface, if we can put some lubricants on the rake and the flank surfaces, then what happens, this friction and the heat generated with the friction can be minimized. Now again, for that lubrication, again you have to give some external means, and you have to use some external agents to bring about the lubricity aspect. So these are very. So now the whole thing is that in the metalworking fluids itself, if we can incorporate both the heat carrying away capacity as well as the lubrication capacity, then that will be very beneficial. Now this mineral oil based metalworking fluids which are being widely used in the metal machining industries, they again possess some issues. So if you can see, a large amount of metalworking fluids are being used. So almost like 640 million gallons are getting used in the metalworking industries. So
Sorry, excuse me, sir. We are not audible, sir.
Sudarshan sir,
Sir, maybe we have lost his connection, sir.
hello.
Yes, sir. It seems that, but he is presenting.
Yes, I'll
sir.
call you.
Yes, sir. Yes, sir. Please. Madam, please switch off your video, ma'am. Sharda, ma'am, please. I request all the participants, please mute your audio and switch off your video so that we can avoid network trafficking. Mrs. Shraddha, ma'am.
Dear participant, please wait. So I informed the research person is going to join within 5 minutes. We lost his connection. Madhivanan sir?
Yes, sir. Yes, sir. I'm audible.
Okay, that's
Yes, yes.
Sorry, there has been some internet issue from my end. So,
Yes, sir. Yes.
now are you able to hear me?
Yes, sir. Very clear, sir. Very clear, sir. Please.
Yeah. So let me again try. I think we were discussing this thing, that
Yes,
what
sir,
are
yes,
the
sir.
problems associated. So when the connection got lost, could you see this screen, or you could not see this screen?
Yes, sir. We
Next
can
slide,
see the
sir.
screens.
Next slide, sir. Next slide. Next slide, sir.
Okay. This was where we stopped, no? So
Yes,
as
sir.
I was telling you that this is the image.
Yes, sir. Yes, sir.
This slide you have explained, sir. Difficulty in grinding,
Okay.
friction,
Okay.
everything.
So as I was explaining that
Yes,
you see these cracks are also formed, and this happens because of the heat which is generated. So because of this, we have to control the heat which is generated. Now, the heat which we can control is basically the friction. The deformation heat we cannot control, but obviously once we employ the cutting fluids, the cutting fluid should have the heat carrying capacity so that it will take away the heat generated due to the deformation process. Now, for the friction part, we can, within the cutting fluid, we can have some lubricants, and these lubricants can come in the interface between the chip and the rake surface and the crank surface of the tools, and they can thereby reduce this friction. But then what we have seen, there is this mineral based metalworking fluids which are used, they also have their own issues. Like, though a lot of metalworking fluids are used, but then their cost is very high. This cost which we are talking about is not just the cost of the raw material of the mineral based fluids, it's also about the disposal issue. So in fact, sometimes the disposal of these, because all these metalworking fluids, they have a shelf life. So after that, you have to basically replace the metalworking fluids. So the cost of the disposal of these metalworking fluids is sometimes even higher than the cost of the raw cost of the metalworking fluids, especially in the countries, in the Western countries, where they have strict environmental laws. For them, you cannot just simply dump this cutting fluid in the soil or in the water resources. So there you have to basically judiciously dispose this cutting fluid. So for that disposal also you may require certain equipment, and that cost is also included in this 18%. And as you can see, because the super alloys, they are more difficult to machine materials, so what happens? This 18% can even go as high as 30%. And now, so this is related to the cost of usage of metalworking fluids. But then there are certain health-related issues also with these metalworking fluid usage. So what happens in many of these metalworking fluids, bacterial growth takes place. So these are some of the names of some of the bacteria which are normally commonly found to grow in the metalworking fluid. And these bacteria, once they grow, they can affect the skin and also lead to respirational problems of the machine operators. So you see, almost, the number is not very small. You see almost like 1 million workers are under the influence of the toxicological. So these are toxicological effects. So these toxicological effects of these metalworking fluids, with that 1 million workers are down with that toxicological effects. And not only that, as I was telling you, if you do not have a proper disposal equipment, you are prone to contaminate the soil, air, or water wherever you are basically dumping the mineral-based metalworking fluids. So then, what is the solution? Because for the for the super alloys, like for material like titanium alloy, so this is a super alloy. So dry cutting is not an option. So this has been found through extensive research that dry cutting cannot be performed. Dry cutting cannot be performed. So this is a problem. So we have to use the cutting fluids or the metalworking fluids. Now, if we go to the left-hand side of this left-hand corner of this particular slide, here I have given a graph showing the useful flow rate of the metalworking fluids which are being used and the applied flow rate. So here there is a very interesting thing which you can observe, that it has been found out by researchers that the useful flow rate is much less compared to the actual or the applied flow rate of the metalworking fluids, which in other words means that we are unnecessarily using a lot of the cutting fluid during the machining or the grinding process. Actually, a major portion of this cutting fluid is not helpful in actually removing the heat. The useful flow means the amount of fluid which is actually involved in taking away the heat, which is our desirable goal. So from this concept, actually, a new thing has evolved, and that is called as the minimum quantity cooling or lubrication phenomenon. So there, what we do, we basically, in spray or mist form, we supply the metalworking fluids. So the same metalworking fluids, but in very limited quantity, and in spray or mist forms, these are being applied, and this spray or mist goes into the machining zone or the grinding zone using some high-speed jet of gases. Normally, we use the compressed air. That means air as the gaseous medium is normally the common media by which we actually ensure that the spray or mist of the metalworking fluid, they reach the grinding or the machining zone. So this is what we are calling as the minimum quantity lubrication technique. Now, in the minimum quantity lubrication technique, we can use the conventional metalworking fluids, but then the conventional metalworking fluids, as we have discussed previously, it has a lot of issues, so environmental as well as health aspects. These are the issues which are with this conventional fluids. So what happens in modern times, we have come up with some novel cutting fluids which we are calling as the nanofluids, and also the cryogen. So like liquid nitrogen. So liquid nitrogen is a cryogenic fluid that is also being used by researchers. So of course, in today's discussion, I will concentrate majorly on these nanofluids, but we have also done some work on the cryogenic fluids also. And we have seen that cryogenic fluids can also help in minimizing some of the issues related with the metalworking, the conventional metalworking fluids. So this can be both nanofluids as well as the cryogen can be a good option and a viable option for replacing the conventional metalworking fluids. But then these nanofluids or the cryogen, it will be more economical, because as you can see, the nanofluids, the cost is a restriction. So nanofluids you cannot use in the voluminous manner, or in what we call normally as the flat cooling manner, which we normally do for our machining activity or the grinding activity. So we have to adopt to this minimum quantity lubrication technique for the effective usage of the nanofluids. So now this voluminous usage of the cutting fluid, which I was referring to, you can have a more better feeling of it by observing these two images. So on your left hand side, this image is about the flood cooling. So we call this voluminous usage of cutting fluid, we call this as a flood cooling mode. So as you can see, a lot of fluid is coming up, and in the previous slide, the graph which I have shown you, you can see here actually out of this large amount of volume of fluid which is coming up, only a small amount of fluid is actually helpful in removing the heat. So on the right hand side, you see this is basically the minimum quantity lubrication process. So here you can see through a nozzle. So this is a nozzle. So through this nozzle, actually a mist of the coolants are coming out, and they are also equally effective in removing the heat. Okay? Here the advantage is the amount of cutting fluid which you are using is very, very minimal. So let us see how this minimum quantity lubrication acts. Sometimes this is given a generic name of minimum quantity cooling and lubrication. That's how this MQCL is coming. But the more popular one is actually the MQL. Of course, there is also a minimum quantity cooling also. Now you see what is the difference between MQL and MQC. The difference is in the cutting fluid which is being used. So in the MQL we use a emulsion type of cutting fluid. So basically a colloidal solution. Say we have water and we have soluble oil. So we mix water with soluble oil, and then we form what we call as a emulsion, which is basically a mixture of this cutting fluid and the water, and it's a colloidal mixture. So this emulsion, when you have this type of emulsion, now this emulsion has both capacity of lubrication as well as cooling. And in MQC, basically you use oil. So mostly in MQC, the oil do not have that much lubrication capacity, which you find in emulsion. So it is mostly used for your cooling application. So that's why it is called as MQC. But the more popular one is called as MQL. So you see here the schematically how this MQL is working. So as you can see, these are the droplets which are coming out, and the droplets are forced into the machining zone or the grinding zone using some air. So the air comes with certain pressure, and that is the reason why these droplets are floating, and it is entering into the intergrid spaces. So these are two grids. So the intergrid spaces, because the droplets are tiny in nature, so they can easily enter into those interspaces, and they can provide the appropriate cooling or the lubrication. Now normally in this MQL technique, as you can see, the MQL technique, you have the small amount of fluid, and this fluid in mist form is actually, it is mixed with the compressed air, and that is what we call as the aerosol. So they form the aerosol, right? Like in our COVID times, we know that this virus may also spread through aerosols. So there are some research activities which tells about the aerosol. So basically aerosol means you have the tiny droplet particles. These are very thin, lightweight particles, and they can float easily in the air. So with the flow of the air, it can go along with the flow of the air. So exactly that thing happens with this MQL process. Now the is normally kept low. So normally it is less than 500 milliliter per hour. Whereas in case of your flood cooling, which we have seen in the previous slide, the flow rate is in terms of some few liters per hour, right? So you have a large, difference in the flow rate. Now, normally it is recommended that this compressed air, the air pressure of this compressed air should be as high as possible, but there is no specific limit of this high air pressure. So mostly it depends upon the restrictions which you have. So you cannot afford to have a very high pressure, because creating that much high pressure, say, will be very difficult. So something around 8 to 10 bars, which is almost like 8 to 10 times the atmospheric pressure, is found to be good enough. And as I was discussing, so you have a boundary lubrication happening because of the mist, the tiny droplet particles entering evenly into the grinding or the machining zone. So a boundary lubrication may get formed, which will lower the friction coefficient. And not only that, the heat transformation also can be improved. And majorly the heat transformation happens in the form of vaporization at the cutting zone, and it is majorly to the convection process. So if you see over here, a lot of researchers have worked on this NQL process using different types of cutting fluids. So these are more or less the standard cutting fluids. As you can see, there is Castrol. So Castrol is a famous oil manufacturer. So their oils like BioCart, this has been also used by researchers. Now you see the whole efficiency of the MQL process can be enhanced if you can use a cutting fluid which is having high thermal conductivity as well as good lubricity properties. Because these are the two essential properties which we require. So if you can tailor your cutting fluid and have a tailored cutting fluid which has both the thermal conductivity and the lubricity properties, then it will be fantastic. Then it can be used more efficiently in the metal machining domain. So let us see how we can solve this issue. So now this, as I have mentioned, that thermal conductivity and good lubricity. Now with this concept, the nanofluids were actually developed. So the nanofluids essentially have better thermal conductivity, and it also possess better lubricity. So this figure explains you how the lubricity can be improved by using of nanofluids. If you see these tiny particles which you see over here, so these are basically the nanoparticles, and these nanoparticles are suspended in a medium which is mostly a fluid medium. So this fluid medium is carrying these nanoparticles. So you have relative velocity. So this is one surface, this is the other surface. So in between these two surfaces, you have a layer of the nano fluid, so which contains also the tiny nanoparticles. So basically, nanofluids are something like you have a base fluid, and within that base fluid, you have some suitable nanoparticles, and the nano-sized particles, they will have typical dimensions as is shown over here. So 1 to 100 nanometers. So this is the typical dimensions of the nano-sized particles which remain suspended in the nanofluid, the fluid medium of the nanofluid. Now these nanoparticles possess certain properties, like they have very high specific surface area, and consequently, because of this high specific surface area, what happens? The heat transfer surface between the particles and the fluids greatly enhances, and that is the reason why a lot of heat can be transferred using these nanoparticles in a fluid medium. And not only that, as you can see over here, as these two surfaces, when they are in touch with each other, and when we have a force acting on the from the top surface, what happens? These nanoparticles, they basically align themselves, and then they form what we call as a mixture boundary lubrication. So mixture boundary lubrication happens. And not only that, sometimes these assembled or coagulated nanoparticles, they can get deposited as a film on the surface, on one of the surfaces. So, and this deposition film is basically a lubricious film which forms on the surface, and they will basically lower the friction coefficient between the two mating surfaces. So this is one surface, this is the other surface, these are the mating surfaces. So you have in between, you have the nanofluid, and within the nanofluids you have the nanoparticles, these black colored particles, and they are getting aligned and they are getting deposited mainly because of this load or force which is being applied in between these two mating surfaces. And then this, if they agglomerate and get deposited on one of the surfaces, what happens? They form what is called as a lubricious film, and thereby they will effectively reduce the friction coefficient between the two mating surfaces. So nanofluids, so you see, the one which we discussed now, that we require cutting fluids which can have both heat carrying capacity as well as good lubricity. So you see, nanofluids is a perfect example of a fluid which possesses both these properties. So definitely nanofluids can be used in the metal machining or grinding domain. So that was the precise motivation because of which we started developing the nanofluids in-house and then using it in our grinding and machining experiments. Now, how these nanofluids can be prepared? It can be prepared in-house. Normally we have prepared in-house only, but you see the nano-sized materials in the form of powders, they have to be procured. So they can be either in a aqueous medium or in some organic host liquids. Sometimes they can be in dry powder forms also. So we have purchased these nanoparticles from outside. So there is a German company from whom we have purchased these nanoparticles. And you see, the nanoparticles, they can be again broadly subdivided into these categories like oxide particles, in which aluminum oxide, copper oxide forms. You have the nitride ceramics, aluminum nitride, silicon nitride. You have the carbide ceramics, silicon carbide, titanium carbide, and you have the metals, which are basically copper, silver, and then the semiconductors. Of course, you have the carbon nanotubes. So carbon nanotubes, they can also be used. In our work, we have mostly used the oxide ceramics because they are comparatively easily available, low cost. So that is the reason why we have used the oxide ceramics. So, of course, some metals also like silver we have also used in our experiments. But frankly speaking, these metals are more costlier than your oxide ceramics. Now the host liquid, that means the best fluid medium, we have kept in most of our experiments. We have kept water, which is like deionized water, not the normal tap water. It's the deionized water, so which is free from any ions within water. So that is what we call as deionized water. So we have used the deionized water as the host liquid medium. And of course, other than water, we could have used ethylene glycol or engine oil can also be used. But these ones we did not try in our lab. Now, what happens? The nanoparticles are normally fabricated. Of course, in our case, we have obtained the nanoparticles. We have purchased the nanoparticles. But just to give you a little glimpse of how these nanoparticles are obtained, so there are both physical as well as chemical processes of obtaining these nanoparticles. So among the physical processes, these are the physical processes like mechanical grinding or milling is also sometimes used, and sometimes inert gas condensation. So the particles, the nanoparticles which we want to make, they will be initially in its vapor form, and then that vapor form will be condensed, and once it is getting condensed, they form very tiny particles which are in the nano levels. So we are not going into the details. These are not very simple processes of obtaining the nanoparticles. There are more inside stories into it, but just I want to give you just a glimpse of how the application of nanoparticles happens. And as you can see, the chemical processes like CVD is very popular chemical process which is used for the nanoparticle fabrication. And you see thermal spray or the spray pyrolysis, these are also very popular in the production of the nanoparticles. Now again, if we come to the nanofluid preparation, we have used this two-step method. But of course, there is one method which is a single-step method where simultaneously the nanoparticles are made and they are dispersed into the base. But here the problem was the production is limited. We cannot produce a large quantity of the of the nanofluids by single-step method. But then the advantage is the dispersion of the nanoparticles within the fluid medium will be very good, and consequently the properties will be also comparatively much better. But then we have to, because we did not have the requisite facilities to make the nanofluids in single-step method, so we have used the two-step method. So where we have used the nanoparticles and then dispersed it into the base fluid. Now this dispersion into the base fluid is to be done by some ultrasonication process. So we have used a bath sonicator. So sometimes food sonicator can also be used, and in this manner the dispersion can be done. But what we have observed that this sonification works well for oxide-based nanoparticles. But when it comes to the metal-based nanoparticles, this particular method is not very suitable. So that is our whatever is our finding. That is, we have not used the other variants, so we cannot comment on the other variants like nitride or thermites. So that we have not used. So now let me give you an image of the photographic images of the nanofluids which have been generated in our lab. So this is silver. So silver nanoparticles. So it comes in a liquid or liquid medium. So the silver nanoparticles, when we purchased it, it is not in powder form. It comes in a liquid medium, and that liquid medium has been mixed with the deionized water. And this L, M, and H, which you see as the subscripts, these actually refer to the concentration of the silver. So L means it's a low concentration of silver, M means a little bit higher, and H is the highest concentration which we have used. So this concentration is not very high. For this high concentration itself is something like 1% by volume, right? So this low percentage is something like 0.01%, because silver nanoparticles are very costly, and one should not waste the silver nanoparticles by putting in more amount of silver nanoparticles, because we have observed that even a small amount of silver nanoparticles in this solution can give very good results. Now, this right hand side is basically zinc oxide. So zinc oxide particles, nanoparticles, were mixed with deionized water, and this is how they. So this is after the sonification process. So they form something like a colloidal solution, as you can see. So the nanoparticles gets distributed within the fluid medium. Now, the one important, so you see, when you have prepared the nanofluids, you have to really just mixing of nanoparticles and some fluid, whether it has really resulted in a nanofluid formation, that needs to be cross-checked and corroborated with further experiments or characterization of the fluids developed. So one important characterization of this nanofluids is that we can measure its potential, which is called as a theta potential. So as you can see over here, so the potential can be obtained, and this is called as a zeta potential of the nanofluid. So what it is, as you can see, this image clearly shows you. So this is the nanoparticles, and the base fluid is somewhere there. So there is a charge, as you can see. There is a charge in between the nanoparticles and the base fluid, and this charge results in some potential difference. So one such potential difference, we call this as the zeta potential difference. So this zeta potential, if it has a particular value, it will ensure the stability of the nanofluids. So when we have made the nanofluids, we have to ensure that the zeta potential value reaches a particular limit. Only then we can call that our nanofluid is a stable nanofluid, and then it becomes fit to be used in the machining application. So that is the reason why we measured this zeta potential. So there are instruments by which you can measure the zeta potential of your nanofluid, and the measurement of this nanofluids, the value of these measurements are shown over here. So as you can see, almost for all the nanofluid which we developed, we have got a negative value, and the threshold negative value is around minus 30 millivolt. So anything beyond minus 30 millivolt is a suitable candidate, and you can tell that the nanofluid, the stability of the nanofluid is maintained, and hence it can be used. So as you can see, in all the cases, we have been able to reach more than this minus 30 millivolt zeta potential. So obviously, these can be used. Now in our case, it's all negative zeta potential, but it can be positive zeta potential also. But again, in positive zeta potential also, it has to be more than 30 millivolts. So plus 30 millivolt or minus 30 millivolts, below or minus 30 millivolt, these are basically the threshold values. So once you achieve above plus 30 millivolt, your stability of your nanofluids is good. Also, if you achieve in the negative side minus 30 or beyond, then also it is stable. So in our case, most of the nanofluids are negative charged values, as you can see. The surface charge is negative, so that is why we find the negative potential. But they are well within the threshold limit, so it can be used. And not only that, see these nanoparticles, the whole issue with these nanoparticles, that they have the problem of agglomeration. So it is basically the Brownian motion which happens within the nanofluid, that the Brownian motion of these nanoparticles is very, very important, because only if the production happens of these nanoparticles, they will not have the tendency to agglomerate. If the Brownian motion did not happen, then what happens? Agglomeration of nanoparticles will start, and of course, once the agglomeration of the nanoparticles starts, so all the benefits we expect from the nanofluids and the nanoparticles, that will get lost. So that is why we cannot afford to have the agglomeration of the nanoparticles, and for that we have to maintain a proper Brownian motion. And again, this proper Brownian motion, whether it is maintained or not, is again like this. So zeta potential, the stability of the nanofluid is obtained by the zeta potential into further physics of this thing, which is basically the Brownian motion. So because of this zeta potential, the Brownian motion will increase, and consequently the agglomeration of nanoparticles will not happen, which in other terms will lead to this conclusion that your nanofluids will be stable. Now the thermal conductivity of the we have seen now that thermal conductivity, which is the heat carrying capacity, has to be high of the metal cutting fluids. So if we want to use the nanofluids as a metal cutting fluid alternative, so the heat carrying capacity has to be high. Now, one way of determining whether the heat carrying capacity of the fluid is high or not is to measure its thermal conductivity. Now, these nano fluids, for these nanofluids, we have the thermal analyzer. So this is a special type of thermal analyzer which can be used for measuring the thermal conductivity of the nanofluids. So the normal conventional got work. So for this, actually, we did not have this thermal analyzer at IIT Delhi. So for this, we had to depend on IIT Guwahati. So IIT Guwahati have such a thermal conductivity analyzer. So if some of you are interested, you can, in later stage, if you want to work on this, so you can actually contact IIT Guwahati Mechanical Department. So they have this thermal analyzer. So they allow others also to use their facility, of course, at a particular cost, which is not very high. So as you can see over here, we have measured the thermal conductivity, and as you can see, we have compared it with the deionized water, which is our base material, base fluid, and we can see that almost for everything, the thermal conductivity has increased. Obviously, once we have more amount of the nanoparticles, the thermal conductivity has increased more. But then as we increase the nanoparticles, the cost factor is one issue which we have to look into. So we cannot use very high amount of nanoparticles because cost will increase. Of course, the benefit in terms of thermal conductivity also you can see is enhancing, but then we have to make a compromise. Also, the viscosity of the fluids have been measured, and as we can see, with the induction of the nanoparticles, what has happened? The viscosity has increased, and as expected, once you have a higher concentration of the nanoparticles, the viscosity increases more. So you see the viscosity at higher things is almost like 4 times that of deionized water, and this can why we are important. We are looking into the viscosity. We are looking into the viscosity mainly because the viscosity gives you an idea about lubricity. So if your fluid is more viscous, it also means that it will have a better lubricity. So that is the motivation why we decided to check the viscosity of the nanofluids developed. So here also, as you can see, we are getting a sufficiently good amount of lubricity compared to the base fluid, the deionized water. Now, other than these properties, we see we have done the pendant drop test to find out the wettability of the fluids developed. So what do we mean by wettability? If you see this particular figure, so you have this over where I am pointing my laser pointer. So this is the surface. So this is the surface, which is basically the carbide tool substrate. So this is the carbide tool surface, and on this carbide tool surface, we have put one drop of different fluids. So the first one is a pure water, the second one is the conventional cutting fluid, and then we have the nano cutting fluids. And we have measured the contact angle. So the contact angle has been measured. So this is the contact angle which has been measured. So in case of your pure water, it has been found to be 71 degree. Now when we are using cutting fluid, the contact angle is becoming narrower. For the nano cutting fluids, the contact angle is even narrower, as you can very clearly see from these images. Now, what is the advantage of these contact angles, and whether higher contact angles or lower contact angles is important? Now, you see, when we are trying to remove heat from a surface by a, say, another medium like a fluid medium, so what we want, that once the fluid medium is sprayed onto that hot surface, what the fluid medium should do? The fluid medium should uniformly spread, or what in other words we call, should wet the entire hot surface uniformly. So if it wets the hot surface uniformly, then what happens? Then it has a better capability to take away heat from all the surface area. So in other words, it means that the smaller is the contact angle between the surface and the fluid, the better it is in terms of weighting of the fluid on the surface. So normally carbides are the tool substrate materials. So you see that the carbide tool substrate will obviously during the machining process or the grinding process will become hot. So now if we can spray these nanofluids on that surface, then what happens? The nanofluid will effectively wet that surface, and it will result in a better heat conduction process. So the conduction and the convection of the process will amplify if we use the nano cutting. So now in this particular table, as you see over here, different types of particles, the nanoparticles. So these are all nanoparticles. So their average sizes are also given here, and the volume fraction. So normally the mixing is done in terms of volume fraction, not in terms of weight percentage. We can also use weight percentage, but normally it is normally reported in terms of volume fraction. And as you can see, that even with very small volume fraction, there can be a good thermal conductivity enhancement. Not only that, if you see, so this is the thermal conductivity part and the weightability part. But if you see in this figure here, carbon nanotubes have been used, and as you can see, with the usage of this carbon nanotubes in some composite coatings, what happens? The friction coefficient has also got reduced. So as you have increased the volume fraction of carbon nanotubes, the friction coefficient has got reduced. So which in other words means the more amount of nanoparticles you have in your material, the better is the lubricity property of that material. Right? Of course, again, a compromise has to be made, because we cannot afford to use very high quantity of nanoparticles. So that is obviously there. But then this is the advantage, that it actually brings down the friction coefficient, and consequently the wear rate also can be lower. So the abrasion wear, which we were discussing in our machining process, that can be lowered substantially when we are using these nanofluids containing the nanoparticles. Now let us quickly go through some of the application areas of these nanofluids. So nanofluids are used both in grinding as well as in machining domain. So we will talk about first about the grinding domain, and then we will move to the machining domain. So here these are literatures. These are not our work. So these are work which have actually motivated us to use these nanofluids in our machining and grinding activities. So as you can see, they have used this nano diamonds have been used. Also, the nano alumina have been used, and they have reported, researchers have reported that with the usage of this nano diamond or the nano alumina, a substantial improvement in the surface roughness achieved. Not only that, in some cases, like when we have used a molybdenum disulfide, so they have used a molybdenum disulfide in their pin-on disc wear experiments. So in between the pin and the disc, they have put this molybdenum disulfide nanoparticles. Then what they have observed, they have observed that this molybdenum disulfide actually resulted in formation of some tribofilm layers, so which is consisting of molybdenum oxides. So some molybdenum oxide layers which are tribofilm layers which get formed on the surface. So in between the two mating surfaces you have this tribofilm, and because of this tribofilm, what has happened, it has been observed that the friction coefficient, as you increase the time duration of the experiment, of the wear test experiment, what happens, the friction coefficient has gradually decreased. And this decrement has happened because of the formation of the tribofilm layers. So the tribofilm initially itself, there won't be any decrement because the tribofilm takes some finite time to form. So as soon as the tribofilm is formed, the decrement in the friction coefficient happens, and consequently the friction force values come down. The heat due to friction force will also come down. So as you can see, nanolubricants have also been used in the grinding test, and in the grinding test we use normally to find out the coefficient of friction, we use the force ratio. That means the tangential grinding force versus the normal grinding force. The ratio of this tangential and the normal grinding force is taken as the apparent coefficient of friction. And it has been observed that by the usage of certain nanolubricants like molybdenum disulfide, there can be a substantial decrement in the force ratio. So basically, which in other words means that your friction coefficient can be lower. And not only that, the abrasive wheel wear decreases in compared to flood cooling as well as the MQL using other standard lubricants like the paraffin lubricant. So again, some more images. So you can see there is another index which we call as the G ratio index in grinding. So what is this G ratio index? It is basically the amount of material removed per unit time divided by the amount of wear happening on your grinding tool. So now if the grinding tool wear is less and the amount of material removed is more, so what it means? It means the G ratio will become higher. So higher is the G ratio, the better it is. So here, as you can see, by using the nanoparticles, you see, nano soybean or the nanoparaffin, so they have been able to achieve very good and very high G ratios. So the coefficient of friction also, if you see, the coefficient of friction can also be lowered. It can be lowered by a very drastic amount. So if you see from here and here, there is a very high drastic reduction in the coefficient of friction. So which is very beneficial. So these are the studies based on which we decided that yes, these nanofluids can be employed in the grinding of the superalloys, and they can be used. So another research paper which we studied gave us an indication about the grinding temperature. If you see the grinding temperature, this grinding temperature again is related to how efficient is the cooling process. So if the cooling process is efficient, the grinding temperature will come down. Now what we observe from over here is that the grinding temperature is again, if you are using the MQL means, then the position of your nozzle, the MQL nozzle, is very important, because based on the position of your MQL nozzle, the temperature reduction can happen. So as you can see, for different nozzle positions, the reduction in temperature is different, right? So here you see, this is the temperature which is produced for a particular nozzle which is tangential to the wheel. Now as you change the nozzle position, what happens? Compared to the dry case, the temperature is is decreasing. Of course, you see in the wet case, so these are all results of the when we have used the conventional fluids. So when we are using the nanoparticle fluids, the results may be even better, right? So in this figure, you see that we are using now the MQL nanofluid mist. So we have different positions of the nozzles, and depending upon the different positions of the nozzles, the efficacy of the nanofluids in reducing the temperature will be different. Now, not only that, the efficacy is also not only just dependent on the position of the nozzle, it is also dependent on the size and distribution of these mist particles which are produced. So these nanofluids, they produce those tiny mist particles. So these tiny mist particles, and these tiny mist particles will also contain the nanoparticles. So, but the tiny mist particles, they contain nanoparticles as well as the fluid media. Now, what is the size and shape of these mist particles? That is also very important. So, for that we developed a setup over here, as you can see. So, we have collected the nanoparticles in an acrylic sheet. And we have also, during this process, we have changed the applied pressure, as you can see over here, and we have observed what is the force obtained. So obviously, as we increase the applied pressure, the force will increase. So again, that is the reason why we cannot use very high applied pressure, because if we use high applied pressure, then again this pressure itself will actually add to the force which is coming up during the machining process. So that is again not very desirable. So we have to again optimize the applied pressure, and we have optimized the applied pressure somewhere around 8 bars. So the standoff distance, that is the distance between the tip of the nozzle and the location where the actual the spray particles will actually come and hit, that is what is called as the standoff distance. So we carried out these experiments taking this standoff distance as 150 millimeters. So this will be the roughly also the experiment. So that is how this entire experiment was developed and designed. And then, as you can see, we have also changed the nozzle locations. And these green dots which you can see, this means that these nozzle locations are fine. So these nozzle locations are fine, but when it comes to the third one, a red dot I have put here. So this nozzle location is not fine, because you can see that the mist which is being formed, it is not able to enter into this grinding zone. Whereas in this case or in this case is the best, because the mist is directly coming and entering into the zone. Here also this rotational motion of the wheel is being taken by the mist, and that is how it is also, the mist is also reaching the interface zone. But in this case, what is happening, the nozzle is located at too high a location, and the mist is getting actually, it is getting diverged out from the machining zone. So it is not able to reach the machining zone. Before reaching the machining zone, the mist is getting diverged out. So this type of location of nozzle, the inkwell nozzle, cannot be used. Also, you see the distance, the standoff distance have also been varied in between the grinding wheel and the nozzle. And as I was telling you, we have tried up to a distance of around 150 millimeter. Now in this of 150 millimeter, the location where we have obtained the lowest boards, that is the location which we have tried to keep. So that is somewhere around 70 72 millimeter. So that this is the location where we are trying to keep the distance. Because you see, if the distance is very large, then also there is a problem. If the distance is very small, there is a problem. So that is why 150 millimeter we could have chosen, but the 150 millimeter would be a larger distance, right? So for this larger distance, we may require for traversing this larger distance, we may require more amount of pressure. Okay, so that was our restriction, that we could not go beyond our 8 bar pressure. So that is why we have to choose this optimum distance as 72 millimeter. Now these are the images of the particles, which are the manner in which the particles are distributed and the shape of the particles. So the shape is important because we want the shapes to be uniform, and also we want it to be uniformly distributed. And here, as you can see, after the analysis, it has been found out that at this particular flow rate of 150 milliliter, we are getting a good amount of droplets, and the percentage of area covered by the droplets is also very high. So that's why for the series of experiments which we have conducted, we have kept this as our optimal parameter for the MQL process. Now we have also tried to find out under these various conditions, we have tried to find out the coefficient of friction. So the coefficient of friction for each passes, we have given more number of grinding passes, and we have seen whether the coefficient of friction is remaining the same or it is varying. More or less, as you can see, there is not much of a variation of the coefficient of friction. Of course, under dry condition, you have the maximum coefficient of friction value, but when it comes to the MQL, so MQL, especially with 150 milliliter, we have seen that the coefficient of friction values have come down. So the experiments over here has not been performed with the nanofluids. It has been performed with the soluble oil. But similar experiments can be performed with the nanofluids to obtain the coefficient of friction. That I will show you later. So these are one nozzle which we have developed in-house for employing this MQL process. So this is the in-house developed nozzle, and this is a commercially available nozzle. And this commercially available nozzle, we have actually modified it and then used it for our present work. We have used both these things, but we have found out that this modified commercially available nozzle has worked in a better manner. So initially we developed our own nozzle, but then the results were not coming that good. Then we purchased this commercial nozzle, and then we modified it a little bit, and then with that modified nozzle, we could achieve a much better results compared to the one which we have achieved with our indigenously developed nozzle. So here is the example. So this is the one where we have used the commercially available nozzle, and the mist, as you can see over here. So we have the fluid flow controller and all those things. So this can be seen over here, and this is the close-up view of the image. And now if we see that when we are doing machining under, say, dry condition and wet condition, so we have used titanium, aluminum, vanadium alloy. So this is the Ti6L for the alloy which we have ground. And when we are grinding it under dry condition, you see a lot of burning marks can be observed. So this is the optical image of the ground sample. You can see this blackish type of marks which you see over here. So these are all the burning marks which you obtain, so which indicates that the surface temperature has become very, very high. In case of your wet, the burning marks are not present, but then there is another issue which is called as redeposition. that means the chips of the work material has got transferred onto the wheel surface, and then again from the wheel surface it has got transferred onto the work or the finished surface of the work material. Now this redeposition is also not very desirable, but because as you can see that this will actually spoil the surface finish. So the surface finish will not be good because of this presence of this redeposition. So this should be also avoided. So the wet condition is giving this redeposition phenomenon. Of course, the wet condition has been able to minimize the burning process. That means temperature can be controlled, but then the redeposition phenomena is occurring there. So this needs to be controlled again. So what we have done, that we have now used the aluminum oxide at different percentages, right? So we have used different percentages of the aluminum oxide nanoparticles. We have prepared the nanofluids and we have used it. So as you can see over here, as the number of passes increases, what is happening for almost all the nanofluids, the aluminum nanofluids, you see that the apparent coefficient of friction is coming down. So the longer time you are grinding, the lower is the friction coefficient. So we have to understand why this friction coefficient is coming down as we are increasing the machining of the grinding time. So that we will understand a little bit later. But as far as the cost analysis is concerned, so we have done a small cost analysis, and as you can see, with the change in the volume percentage, you see the cost also changes. So from 0.5 to 1%, if we make, there is a huge change in the almost twice. So the most economic one is something like this, as you can see, 0.05%, and 0.05% is also giving a very decent reduction in the friction coefficient value. So now we have also tried copper oxide. Now in copper oxide, the issue is that with increasing the number of grinding process, the friction coefficient is not reducing that drastically. If you see, compared to this, it is reducing. From 0.35, it has become almost like 0.25. But then when you see over here, so there is not much of a reduction. So something like it is 0.35, and then you have 0.3. So not much of a reduction is happening in the copper oxide. So also here also, if we see the copper oxides are a little bit more costlier. So if you compare cost wise also, the copper oxide is not much favorable. Now let us see why in copper oxide there has not been any appreciable change in the friction coefficient, whereas in the case of your aluminum oxide there has been an appreciable change in the friction coefficient. So let us understand that. For understanding that, we have to go to the ACM images of the ground surface. So here, as you can see in this ACM image is of the ground surface where we have used the aluminum oxide nanofluid, and you can see there is a white layer over here. So this layer which you observe over here, which we discussed previously also, that was a layer of molybdenum disulfide. Now here there is a layer of aluminum oxide. So a layer of aluminum oxide, so a tribofilm of aluminum oxide is forming on the surface, and this is the reason why the friction coefficient has got lower, because of the formation of this tribofilm. Now in case of copper oxide, because in aluminum oxide the advantage was that the aluminum oxide film will have a whitish color, whereas in case of copper oxide the film will not have a whitish color. So that cannot be distinguished over here. So maybe in case of copper oxide also maybe a tribofilm was more, but then the tribofilm was not very effective, because as you can see the tribofilm, the copper oxide tribofilm has a lower melting temperature of around 1100 degrees centigrade. So roughly this is the temperature, instantaneous temperature, which you may expect when you are grinding titanium alloys with the conventional grinding wheels, and possibly because of this, that the ribofilm which was formed could not sustain the temperature, and that was the reason why the copper oxide has not been able to show any reduction in the friction coefficient with the grinding time. Whereas in case of the aluminum oxide, the aluminum oxide ribofilm layer is very stable even at higher temperatures. So that was the reason why it has been able to sustain the temperature and provide better lubricity as grinding time progressed. Now we have done some EDAX analysis to confirm this presence of the oxide layer. So as you can see, for the dry condition, we have done some EDAX analysis. So here again, silicon and carbide, because we have used a silicon carbide conventional wheel, so we have obtained some silicon and carbide peaks in the EDAX also. So the mass percentage of these materials is shown over here. So we can conclude that oxygen has come up in the ground surface mainly due to the oxidation produced because of the high temperature, and grits fracturing has happened, and some kind of oxide layer has also formed in case of the dry condition. But this oxide layer is not a ribofilm layer, so it has not helped in the reduction in the friction coefficient. Now in wet condition again, there has been some oxidation because oxygen was present. Grit fracturing has happened, but comparatively its percentage is much less compared to the dry condition. And also here high amount of titanium we can observe. So the titanium content is more on the ground surface, which is actually desirable. So this means that not much titanium has. So there has not been any redeposition. Redeposition in the sense that redeposition or deposition of the what material can happen on the workpiece or on the tool side also. So this has not happened because the titanium present on the ground surface is quite high. Now when it comes to aluminum oxide, here you see the clear evidence of aluminum and oxygen on the surface proves that ribofilm has been formed. And also the titanium percentage is less on the surface because you have the aluminum and oxygen ribofilm. So that is the reason because the EDAX can only take up to a particular thickness. So beyond that thickness, if some material is inside, that cannot be captured by the EDAX process. So that is the reason why you don't see the titanium percent. You see the titanium percent has reduced in the case of your aluminum oxide nanolubricant. Now here again also this copper oxide on the surface proves that ribofilm is also getting formed in case of your copper oxide. But then, as I told you, that possibly this ribofilm is not that effective as that of your aluminum oxide, mainly because its temperature, the temperature at which it can sustain, is comparatively much lower compared to the aluminum oxide. Now coming to the hardness, so what we have done for different conditions, we have ground the specimen and we have taken the hardness values. And as we can see, the initial hardness of the titanium alloy is somewhere around 349 Vickers hardness. Now in case of dry condition, what has happened? The average hardness has decreased to 303. So this is mainly because of the high temperature generated during the machining, during the grinding process, which in turn has lowered the hardness. Now in wet condition, the hardness is little bit more than what we have observed in dry condition, which indirectly indicates that in wet condition the temperature was comparatively lower. But then when it comes to the nanofluid, you see the hardness values after the grinding process is considerably high, which which means that these aluminum nanofluids have been able to effectively control the temperature. So the temperature rise on the surface of the ground specimen was not that much, and because of that, the hardness of the surface has not been compromised compared to the initial hardness. Now, if we see the surface roughness, you see the surface roughness with aluminum oxide or MQL with copper oxide, the surface roughness is not that good. So then is it bad or is it good? Because we expect good surface roughness in case of your grinding process. Now here I would like to let you know that the grinding wheel, the abrasive size which we have used, is not supposed to be the abrasive size which is to be used for a very good smooth surface finish. So if we really want to have a very high surface finish, we have to use very low grit size. Whereas in our experiments we have used a moderate grit size, which has the capability to remove more material rather than giving a better surface finish. Now, this higher roughness has happened mainly because of this, that the grit sizes in the wheel which we have chosen was on the higher side, and since the grit sizes were higher, what has happened, and the grits have also not got fractured because of the high temperature. The grits retained their sharpness, and consequently the sharper grit has resulted in higher surface roughness. So if you see in the wet condition what is happening, or in the dry condition what is happening, the surface roughness is decreasing. Why it is decreasing? The surface roughness is decreasing mainly because with passage of time, what is happening? The grinding grits are getting fractured and they are getting dulled, and consequently the dulled wheel is not removing material, but it is rubbing on the workpiece material, and this rubbing phenomena is leading to a better surface finish. That's why in these dry or wet conditions you are finding good surface roughness, but in the case of your nanofluids, you do not expect that type of better surface roughness. With this particular wheel, maybe if we want to achieve a better surface roughness, then we may have to use a finer grit size with the nanofluids. Now we come to the, so far I have discussed about the usage of nanofluids in the grinding process. We have also used these nanofluids in the machining process, mainly the turning process. So some superalloys like pneumonic superalloy has been used for these particular experiments. So we have used over here majorly the alumina nanoparticles, and we have also used a biodegradable emulsion like sunflower oil. Instead of using the conventional cutting fluids, we have used a biodegradable emulsion like sunflower oil. Sometimes we have used also castor oil also, as so. Now the MQL parameters, we have used various MQL parameters. The air pressure, we have kept it a little bit on the lower side, and the fluid concentrations also we have changed. But for the alumina, that means the nanofluids, the volume percentage of alumina in the nanoparticles inside the deionized water is almost in the same range as we have used for the grinding experiments. For the colloidal silver solution, the percentage of volume is kept a little bit on the higher side. So these are again the images of the nano fluids, as well as the sunflower oil biodegradable fluid which has been developed in-house. Now this is the variation of cutting forces with cutting length. So as we increase the cutting length, how the cutting forces have behaved. So we have got both the main cutting force as well as the feed force. So feed force is always lesser than the main cutting force, which is normally the case also. But as we can see that as we have increased the cutting length, maybe because of the wear of your cutting tool, the single point cutting tool is wearing out, so it is losing its geometry. So consequently, the forces have increased. Now, when it comes to the nanofluid, so this was under dry cutting condition. Now, when it comes to the biodegradable fluid or the nanofluids, here you see that the forces which has been found out, the forces are comparatively much lower compared to what we observed in the dry case. Okay. So in case of your aluminum oxide, definitely the forces are much lower. In case of your silver, the forces are more or less in the, but depending upon the flow rate which we have used, we can get some benefits even by using the nano silver particles. But of course, using the nano alumina fluids, we are achieving a very good result that the cutting forces are coming down. So let us understand what is the reason why this reduction in cutting forces are happening. So there are various proposed theories or mechanisms by which these nano fluids are able to lower down the forces. So one is basically the ball bearing action of these nanoparticles. So nanoparticles, especially if they are in spherical in shape, what happens? They can enter into the interface between the chip and the tool, and these are small spherical nanoparticles. So they will act like roller bearings, right? So like ball bearings. So roller ball bearings, they will act like that, and consequently, they will basically change the the surface friction into rolling friction. So the sliding friction gets converted into rolling friction, and as we know, rolling friction, the coefficient of friction in rolling will be always lesser. So this is one way that the nanoparticles can actually improve the friction between the chip and the tool, and consequently the friction forces can be lowered, and effectively the cutting force will come down. Not only that, if we are using the cutting fluid, what happens? This nanoparticles, no, they actually play a role. For example, if we see this figure, so if you have a hot plate, what happens? As soon as the liquid drop comes, the liquid drop immediately at the interface between the liquid drop and the hot plate, it forms a vapor jacket. Now, as soon as the vapor jacket is produced, we know that gases are not very good conductors. So this vapor jacket will act as insulator, and it will not allow any transfer of heat from the hot plate to the liquid drop. Now, in the case of when we are using nanoparticles along with the liquid particles, so what is happened then? That nanoparticles is actually effective in basically piercing this vapor jacket. So the vapor jacket which is produced, or this bubble which is produced of this vapor, so this bubble is getting pierced by the sharp nanoparticles, and consequently again the contact between the liquid droplet and the hot plate is re-established, and this entire phenomena we call it as the Leidenhorst effect. So because of the Leidenhorst effect, what happens? The nanoparticles will be able to penetrate inside the vapor layer, and consequently will aid in better removal of heat from the hot surfaces. Also, the nanoparticles, as you can see, suppose the tool has worn out. So on the wear out zone, the nanoparticles can come and can get deposited, and it forms an effect which we call as the bending effect. So basically, it basically repairs the worn out surface of the cutting tool, and consequently the cutting tool preserves its sharpness, and as a result, the force can be also lowered. Also, as we have seen that sometimes these nanoparticles, because of the temperature and the forces coming up, they can produce some tribal layers, and these tribal layers again can reduce the frictional component of the forces, so thereby the forces can be decreased. So that is how you see the usage of the nanofluids during the machining process can help in minimizing of the cutting process. Now, not only the cutting process, the wear on the tool can also be actually minimized, and that is what is being shown by these ACM images. So as you can see, in dry condition, fracturing of the tool edge has happened. In case of the sunflower oil, you don't have fracturing, but you still have some pit formation happening on the blank surface of the tool. In case of your nano, when you are using the nanofluid, aluminum oxide especially, you don't observe such pit formation. Of course, the regular wear patterns can be seen. So this obviously will happen because once you are machining and cutting, wear will take place on the flank surface. But then there is no catastrophic phenomena like fracturing or pit formation. Now, in case of silver nanoparticles, one important interesting observation was that there was some adhesion of material on the tool surface, so which is actually not very desirable, and this shows that the silver nanoparticles may not be very effective nanofluid if it is used during machining of this mnemonic-based material. Now, the one which we have shown was the flank surface. Now we are going to the rake surface. So here again, you see in the dry condition, a lot of adhesion is taking place for the dry or the sunflower oil conditions. For the alumina, again, the tribofilm layer was formed, which has helped, and this has been again proved by the EDX method. In silver, again, you see some chip fragments have been observed on the rake surface of the particles, and this again points that the silver nanoparticles could not actually resist the adhesion problem, so could not address the adhesion problem. So even if you are using silver nanoparticles, the adhesion will take place. So adhesion will happen. Now, some more work on this. So we have the nanoparticles here again, like what we have done for the grinding operations. We have again studied the contact angles for the nanoparticles or the nanofluids which we have developed. Again, you see the nano alumina particle. It is giving the best contact angle, so it will have better spreadability. And if you see the nose wear, again you see the nano alumina particles. In nano alumina particles, the nose wear is very, very negligible. Here we have also used, instead of sunflower oil, also we have used castor oil also, which is again a biodegradable oil. So our focus was, one of the focus for these experiments was to obtain a sustainable cutting fluid. So of course, this nano fluids we can also call this nano fluids as sustainable ones. Now this is the rake phase we had, which we have measured at some other cutting velocity. 80 meters per minute for mnemonic is quite a high speed operation. So here again you see for dry condition there is a lot of adhesion taking place, but for the nano fluid aluminum oxide, the adhesion is almost negligible. In castor oil also you see adhesion is there. Sunflower oil, though they are biodegradable oils, but even then they are not in a position to perform that well. Now coming to the conclusion, so these are some of the glimpses of the work which we have done at our lab at IIT Delhi. So if we conclude from whatever I have shown today, So what we have been able to understand is that when we apply MQL is definitely a better process to apply the cutting fluid. But before applying the MQL, we need to basically optimize some of the MQL parameters like nozzle distance, standoff distance, the pressure which is to be used, the flow rate, so that we get good quality droplets. So these are something which we have to basically prefixed and then only use the MQL method. The droplet quality we could measure using the microscopic and the image processing techniques. You see the MQL technique. MQL technique was initially adopted for the machining process, but now this MQL technique is also very effective for the grinding process also. That this is one thing which we have been able to establish. And also this nanofluids can be a sustainable fluid, and it can be a good cost-effective alternative to conventional cutting fluids, provided we use the nanoparticles carefully. For example, it is better to use the aluminum oxide nanoparticles. This nanofluid, aluminum oxide compared to copper oxide, aluminum oxide performs better. It is cheaper, so it also performs better. So it can be very widely used. The nanofluids has been able to maintain surface integrity. That means the hardness results show. Of course, we could also do a residual stress calculation, and from that also we can conclude that the nanofluids, usage of nanofluids will result in lower residual stresses. So that part I have not shown you. That part also we have done. We have calculated the residual stresses, and we have found that when you are using nanofluids, the residual stresses inside your work material is comparatively much lower. And the important one is this nanofluid sometimes forms Taibo layer, which will be beneficial in reducing the frictional forces, and that is the reason why with progress in time, the aluminum oxide has been able to deliver even better results compared to the other nanofluids. Of course, the part which is still remaining is basically the wheel. Of course, in some later work we have done wheel analysis also. That means after usage of these nanofluids, we observe how much wear has happened on your wheel. So that we have done later on, but those results I have not shown over here. So this is one aspect which we can always look into, and of course this aspect of G ratio we have not performed. So this is a open-ended thing which can be looked into and which can be researched. Also, the nanofluids can be used, and the results are quite encouraging, especially when we are using the nanofluids for our mnemonic type superalloy machining. So with this, I want to conclude today's talk. And if you have any, I have given the references. So, and if you have any questions, you are welcome to ask me, and I will be more than happy to answer your questions. Thank you.
Thank you, sir. Thank you, sir. It is a really excellent presentation, sir. As you said, we will go with the question and answer session, sir. I request the participants, please unmute yourself. You can ask directly to our professor, or you can type your question in the chat box. We will ask on behalf of
you. Hello, sir.
So I am stopping sharing my presentation. Yes, please.
Hello, I am Dr. Orko Chaudhary from Haldia Institute of Technology, West Bengal. I want to know.
Okay, very good.
You are telling about that zeta potential.
Yes.
Because of zeta potential, there is a Brownian motion, and which delays the agglomeration. Now,
yes.
Just I wanted to, maybe I missed or something. Now, as the zeta potential increases, the Brownian motion increases, or what? That I
Yes,
want.
that is precisely the reason why we should have that threshold value, that 30 millivolt or minus 30 millivolt. So
Oh.
either we should be, if it is a positively charged nanoparticle, it should
Oh.
have a potential more than plus 30 millivolt on the surface, or if it is a negatively charged one, it should have a potential more than minus 30 millivolt.
Oh, acha. Means if it is more than 30 or I mean less than 30, then the Brownian motion will increase.
Yeah. Yes, because it's just the sign is basically, don't go by the this thing. Sign is basically whether the charge is negative or it is positive. But
Acha.
it is the value. So basically the modulus is important.
Okay. Okay. And sir, another thing is, what is this tribo layer? What is
Tribo layer is basically an aluminum oxide layer which is getting formed on the surface of the material. So it can be the wheel material, it can be on the work surface material. The images which I have shown is on the work surface material, right? But it can also be formed on the wheel surface. But we have not taken because our wheel was very large, so taking it inside the STM was not possible. That is the reason why there was this physical restriction and we could not take the image of the wheel. But it would be very interesting to see the wheel image also, because the tribo layer can form on both surfaces also.
okay? Okay, sir. Thank you.
Yeah, I was seeing somebody has written something, I think. Just here, whether any vegetable oil-based coolant has been found good for machining titanium alloys. So this area actually we have not attempted this, right? So this vegetable oil which I have shown you was only attempted for the mnemonic material. It was not attempted for the titanium alloy. So this is like an open field. So if you are interested, you can work on it and you can yourself understand whether it is good or bad.
Thank you, sir. I
Yeah,
request,
yeah, that's good. You have tried some lubricant, like ghee. So that is good. That is where we should actually, we need to evolve out new cutting fluids which are biodegradable, which are not hazardous. Neither should be hazardous to the machine operator, nor it should be hazardous to the environment.
thank you, sir.
Hello, sir.
Okay, so
Yes, sir.
aluminum oxide is more efficient than copper oxide. Yes. So here, as I am telling you, that copper oxide, we tried copper oxide with this conception that since it has got better conductivity, it should work in a better manner. But then, as we have observed, that it is the tribo layer which is playing a crucial role actually. More than the thermal heat carrying issue, it is the tribo layer formation which is playing a more crucial role. And in this respect, aluminum oxide excelled in the sense that it produced a tribo layer which has a better sustainability compared to the copper oxide tribo layer. Right? So that is precisely the reason why the aluminum oxide, though it has lesser thermal conductivity than copper oxide, the aluminum oxide has been able to perform better. Yeah, this negative rake, what would be the implications on cooling? See, negative rake normally in machining, negative rake is not normally recommended, because that negative rake, as you can understand, the flowability of the chip will become difficult and this will raise the cutting forces. But then negative rake needs to be provided if you are machining with a brittle type of tool material. So if you are using a brittle type of tool material, then definitely negative rake you need to use. So it depends upon what material you want to use and what is the tool material which you want to use. So negative rake, definitely if you are using the cooling method, negative rake, no? So if you are using a negative rake, then the cooling, because the heat generation will be more, so you need more cooling, and consequently you also need better penetration of your cutting fluid. So you need to adjust the parameters. Like if you are using MQL, then you need to adjust the MQL parameters, like the pressure of the air with which the droplets are going. That needs to be actually, it needs to be again optimized.
Thank you, sir. One more question from Professor Gurlingam, sir. Whether any machine tool is available with the MQL features?
See, normally MQL feature, as we have found out, that MQL, you see, it can be a separate system which you can indigenously develop, and you can actually, depending upon the type of machine tool which you have, you can actually integrate it with it. But I think these days, if you are purchasing a new machine tool, maybe you can have a dialogue with the machine tool manufacturer, and the machine tool manufacturer themselves can provide you as an optional accessory the MQL setup.
Thank you, sir. Professor Naresh, sir, you can ask questions.
Thank you, sir. Hello, sir. Good afternoon.
Yes.
This is Naresh, research scholar from
Okay,
Albert
good.
campus, sir. It was a nice presentation, sir. I got only 2 questions, sir. One question is about using of this biodegradable lubricants, sir. There is sunflower oil, castor oil, and one of the professors said they also tried ghee.
Right.
So whether it is suggestible to go with these biodegradable materials which are being used for other food applications in factory, because it may lead to the situation that it may create the shortage
I have not told you. Sometimes what we have seen now, these biodegradable oils, they tend to actually under the machining heat, they tend to actually disintegrate, right? So this disintegrated product, that may not be actually sustainable, so they may be dangerous also. So when we are using these biodegradable fluids, we have to be very, very careful, and we have to also keep an eye on the type of temperature which is getting generated during our machining or grinding process. In fact, in grinding process, since the temperature is more, then some of these biodegradable materials should not be even attempted.
Whether it is going to affect the tribolayer formation because of these biodegradable oils, because the water may not be having any problem, but coming to this
No,
biodegradable
actually, see, this is the problem, that if you are not using the water, and if you are using only the biodegradable oil, then again this cost wise, it may not be very effective, because the cost will increase.
Okay. One more general question about nanofluids.
Yeah.
So we are using nanoparticles into the dispersing into the fluid, and we are using as a nanofluid for cutting fluid heat dissipation. So whether it can be recyclable, or how many days it will life of shelf life, how many days we can use that, and how we are going to dispose or handle this one after usage.
Yes. So this is a good question actually. Since MQL, you see, MQL we give very small amount of fluid, and there is no recirculation happening. So whatever fluid we provide during the MQL, that gets lost. So we do not have any means of basically recirculating the nanoparticles and taking it. But since we are using MQL only, so the amount is very less. Of course, this shelf life, because this nanofluid which you have made, it again has a particular, say, around what we have seen, around 2 to 3 weeks is normally. So if we have made the nanofluids and if we have kept it, after 2 to 3 weeks, we have seen that there is a good amount of settling happening. So settling is happening mainly because the nanoparticles are then coming down and they are not getting now dispersed. So normally the shelf life, if I have to answer your question, is around 2 to 3 weeks. But again, this shelf life can again be increased by changing some of the things, like this nanofluid which I have mentioned. This is not just nanoparticles, and so we have some surfactants also. So the nanofluids cannot be just made by mixing nanoparticles and the base fluid. you have to use some surfactants. So the surfactants role is also very important. And what is the quantity of surfactant which you are giving? That will also determine the shelf life of the nanofluid.
Can you please suggest which are the most used surfactants?
Which are the
Most used surfactants for doing so?
surfactants? We have used the SDBS. So SDBS is the most widely used surfactant. So that is what we have used. But of course, the percentage is how much of the SDBS you have to use. That is a trick. So that you have to carry out experiments and find out.
One more last question, sir. So
Yes.
what about the safety of the operator? Because it is being used in nanofluids and aerosols also created, you mentioned in meeting, and it is going to be a very fine mist actually. So it
Yes.
may also
Right.
flow in air and also come into operator because accidentally. So how we can
Yes.
handle this situation?
Yes, that is the reason. If you see, that is the reason why we always prefer to use as low concentration as possible. You know, in US, they have this thing that they still consider that nanofluids are not that biosustainable fluids, right? And that is precisely because of the concerns which you have raised. And that concerns we also did have. And that is the reason why we thought that if we can minimize the concentration but get a desirable, maybe not the best, but a desirable benefit, then that is how we worked on.
Okay. Thank you, sir. Thank you very much, sir.
Thank you.
Thank you, sir.
Good afternoon, sir.
Yes,
yes,
good
ma'am.
I
afternoon.
have one question.
Yeah, please go ahead.
I'm a research scholar and from biological field. Actually, I am working on a nano emulsions.
Okay. Good, very good.
And so, sir, I want to ask you that nano emulsions and nanofluids are the same thing or the different thing?
No, see, this nano emulsions will be a separate category, because the type of colloidal solution which we obtain, in this case, as you can see, the nano emulsion is supposed to last for a longer duration of time, right? Whereas, as I am telling you, that nanofluid which we develop, that after a particular time period, so that has a shelf life. So after a particular time period, the nanoparticles will gradually starts to precipitate.
Yes.
So in fact, the nano emulsion, you can make the nano emulsion. And nano emulsion, in my opinion, the nano emulsion will have better shelf life and it will possibly provide better efficiency, even if it is being used in our material context.
Okay. Thank you, sir.
Thank you. Yeah, any further questions? Is there any further question or?
Sir, excuse me, sir. Sir, Madhivanan, sir, are you audible,
Yeah,
sir?
please tell me. Hello?
Sir, 1 minute, sir. 1 minute, sir.
Okay.
Right, sir.
Right.
So there is one more question in the chat box, sir. Sir,
What
can I read, sir? Sir, can nanofluid be useful in bearing applications as a lubricant?
Yes, they are very useful actually. They are very useful and people are using it. In bearing applications, they are using it. So sometimes, solid lubricants, So solid lubricants in the nano form, say molybdenum disulfide, that is the solid lubricant. It can be in micro form, it can be in nano form. So people are using molybdenum disulfide in nano form, and that is being used in the for bearing applications as lubricant.
Yes. So one more question is there, sir.
Yes.
Tell the facility where to measure wettability property.
Wettability property, see, this wettability property, basically the contact angle can be measured, as I have told you, no? The pin and drop test. So if you have that equipment, no? Where we can do the pin and drop test, so basically a goniometer and basically a focused camera. So you can take the one drop you can put on the surface on which you want to measure the wettability, and then you take a image of it, and then using the softwares you can find the contact angles.
Sir, one more question from Naresh, sir. So, where it is possible to replace this liquid lubricant with a solid lubricant, all machining operations?
See, this liquid lubricant with solid lubricant. See, solid lubricant in machining, solid lubricants will give you a pure dry machining condition, right? That will be a more sustainable machining condition. This nanofluid application cannot be totally called as a fully sustainable one. It is because we are using lesser amount of nanoparticles. That's why we are claiming that it is moving towards sustainability. But we cannot, as of now, we cannot say that this nanofluids is totally a sustainable fluid. Whereas when you are using the solid lubricants, it gives you a very sustainable environment.
Sir, good afternoon, sir.
Yeah.
Sir, I would like to ask one question, sir.
Yeah, please.
In order to purchase the nanoparticle, any license is required, sir?
No license is required. Actually, there is one AICTE Nano. So there is a one company which is the Indian agent. So from them I have purchased it. The main manufacturer of the nanoparticles is actually a German firm.
Which company, sir? Can you repeat once again?
AICTE Nano. REINSTE, AICTE Nano. So this is the name of the company. So you can find its website also, and you can contact them, and they can. So for this, you don't require any permission.
Okay, thank you, sir. Sir, one more question, sir.
Yes.
Can you suggest what is the name of the device to measure the viscosity, sir?
So that is a viscometer, actually.
Viscometer.
Viscometer.
Oh,
These are the new ones. You have more advanced viscometers where you can basically, once you test it, all the data and everything, and including the analysis, will come in a software. So you can get the software, and from that software you can get your results.
Oh, thank you, sir. Thank you, sir.
So I think one more question is there, whether work hardenability in machining of superalloys is still a challenge in the industry. Yes, it is a challenge. Now, how best we can address this issue? You see, one way out is basically reduce the forces, reduce the cutting temperature. So in this way, if you can reduce the forces and the cutting temperature, then this work hardenability can be to a certain extent minimized. But you know, it is the inherent property of the material. So you cannot totally eliminate the work hardenability. You have to bear that work hardenability, that okay, this material will have work hardenability. But you can only give your efforts in trying to minimize the work hardenability. See, the software which are used for using the angles, these are basically the image analysis software. So you have a number of this type of software. So the best thing is basically to capture the image. So once you have a CCD camera fit in your system, pen and drop system, then what happens? It captures the image. So the drop, how it has formed on the surface, that image is being captured. And once that image is there with you, you can use any standard measuring softwares to measure the angles.
Thank you, sir. Sir, shall we go with vote of thanks, sir?
Yeah. Fine. If there are no more questions, and also I can tell all the participants and whoever is interested, you are welcome to email me. Normally, I respond to emails very fast. So So I would request you that if you have any queries even later related to this area or related area of research, you are always welcome to contact me. My contact address and email address you will get in the IIT Delhi website. No? So that from there you can contact me and I will definitely respond. So there is no issue.
Thank you, sir. Thank you. Thank you, sir. It is a really very informative session, sir. And you have given machining process using nanofluid, application of nanofluid, and a lot of things. Like you have started with problems, difficulties in grinding, and how we can use the nanofluid, and what are the possibilities. Everything you have shared, sir. And thank you very much, sir. Actually, this information what you have given, it is very useful for all participants, particularly for research scholars. A very useful session, sir. And now I request our convener to conclude this.
Then I am
Yes,
extremely
sir.
sorry for the internet disruption which has happened. So I am extremely sorry. So that has created a little bit of disturbance, but I do not know why it has happened. Normally, the internet is stable, but sometimes these things it is beyond my control. So that is one thing.
But
No problem.
But we have received complete information, sir. Thank you, sir.
Sir, good afternoon, sir. Myself, sir, I am the convener of this program. Good afternoon, Professor.
Okay. Thank you. Thank you for giving me the opportunity to share my things with the audience, actually.
Sir.
Yeah.
Myself, Dr. M. Chandrasekhar Reddy, convener of this STTP, on behalf of management, principal, Department of Mechanical Engineering, and participants, thank you very much for accepting our invitation and delivering webinar talk in AICTE sponsored STTP on nanotechnology and functional materials, organized by SV College of Engineering, in spite of your busy schedule, and enlighten the participants in nanofluids and applications. Sir. Thank you very much, sir. Thank you very much. Accepting through mail itself, sir. We are not contacting you.
Thank you. Wishing you all the very best. I think you have another 2 days of your this program is still going. So yes, my best wishes to you and all the participants. Thank you.
Thank you very much, sir. Thank you very much, sir. So
thank you very much. Thank you, sir. Dear participants, our morning session is over. We will meet again 1:45 p.m. for the next session from Professor Kaushik Paul from Indian Institute of Technology, Roorkee. The topic is recent advancement in nanomaterials. Thank you all.